Hey there, and welcome. Today, we are going to unbox a concept that is, no joke, the secret engine behind just about everything, from your Spotify playlist to the latest AI. We're talking about vector spaces. Now, I know it sounds a little intimidating, but trust me, stick around and you'll see it's actually a really beautiful and powerful idea. Let's dive in.
Okay, so let's start with a little thought experiment. Imagine you've got this mysterious black box. You can put something in on one side, that's your input, and then poof, something else comes out the other side, your output. You can do this all day long, trying different inputs, but you have absolutely no idea what's happening inside that box. It's a total mystery.
So, that's the big question, right? How in the world do we figure out what's going on in there? How do we crack the code and understand the rules that make this thing tick? Well, that's exactly what we're going to do. We are going to pop the lid off this thing and see what's inside. All right, time to pull back the curtain. See, to really understand what's in the box, we need to learn its language. And that language, it turns out, is linear algebra. It's what gives us the words, the vocabulary, to describe exactly what's going on under the hood. And here it is. This is the grand reveal. All that vague stuff we were talking about, it has precise names. Those inputs and outputs, we call those vectors. That mysterious black box doing all the work, that's what's known as a linear transformation. And the entire world, the whole system where all this magic happens, that is a vector space. Just like that, we've swapped out a mystery for a clear mathematical framework. Okay, so we've just named the most critical piece of the puzzle, the vector space. So let's zoom in on that. Let's take a look at the actual blueprint. What is this structure that's holding this entire system together? You know, when you really boil it down, it is shockingly simple. A vector space really only has two main ingredients. First, you have a collection of things, a set of elements that we call vectors. And second, you have two and only two specific things you can do with them. You can add them together and you can scale them. That's it. It's just a bunch of stuff and two rules for playing with it. Now, to make sure this doesn't feel too abstract, let's bring it down to earth with an example that I bet you've already seen. We're talking about the good old two-dimensional plane from high school geometry, you know, with an x and y axis. Mathematicians have a fancy name for it, r squared. So on this 2D plane, any points, any coordinate, like 1, 2, can be one of our vectors. And what can we do with it? Well, we can add two of them together, just like you see here, and we can also multiply one by a number to scale it, basically making it longer or shorter. And because we have a set of things, our vectors, and we can do these two operations, this simple 2D plane is a perfect, classic example of a vector space. But here's the thing. For any of this to be useful or reliable, it needs to follow a consistent set of rules. You can almost think of them as the laws of physics for this little mathematical universe we're building. These rules make sure everything works predictably every single time. These fundamental rules are called axioms, and really, their whole job is to act as guardrails. They guarantee that the system behaves in a way that just makes sense. They prevent any mathematical weirdness or chaos, which allows us to build all sorts of powerful tools on top of this foundation, feeling confident that it's not going to crumble underneath us. For addition, the rules are pretty much common sense. They basically say that when you add two vectors from your set, the answer you get is also in that set. It doesn't matter what order you add them in, and there's always a zero and a way to reverse your addition by adding an opposite. See? Pretty intuitive stuff. The rules for scaling are pretty similar. They just make sure that multiplication and addition play nicely together. When you put all these rules together for both operations, they guarantee that our vector space is this stable, predictable environment where the math just works the way you'd expect it to. So let's do a super quick recap. We've got our set, which is just all our possible vectors. We've got scalars, which are the numbers we use for scaling. The vector space is the whole shebang, the set plus all the rules. And that linear transformation? Well, that's our black box, and it's not a mystery anymore. Okay, so this is the moment. We've gone through all this abstract math. But why? Why should you care? What is the big deal? Well, this right here is the payoff. This is where we see how this idea literally shapes the world around us. Honestly, it's wild. Vector spaces are everywhere. In machine learning, every single data point, say all the features of a picture of a cat, is treated as a vector. For data scientists, huge data sets are just giant vector spaces. The sound waves for the music you're streaming, the 3D models in a video game, even states in quantum physics. All of it is described and manipulated using the language of vector spaces. And so we've really come full circle, haven't we? We started with this confusing black box, a process we couldn't understand.
But by applying this framework, by learning this language, we've turned that mystery into a predictable, manageable, and incredibly powerful system that lets us build some truly amazing technology. I want to leave you with this one last thought. Vector spaces aren't just some dusty definition in a textbook. They are quite literally the language that modern science and technology is written in. Once you learn to spot them, you start to see them absolutely everywhere. So, think about it. What other black boxes in your world could be unboxed if you just had the right language? Thanks so much for joining me.